Hi, Algebra 2A students, it's Miss Carol again, and I am back for round 2, Project 1, Lesson 2 video. This time we've got 6 questions. So let's just jump right in. Princess Polly is studying real and complex numbers and analyzes a set of expressions using what she knows of complex numbers and quadratics to evaluate several expressions. So for the first one, Princess Polly thinks that the product of 5 plus 3i and 6 minus 4i gives a real number, which is written as 12 plus 0i. Okay, so let's just go ahead and use the FOIL method to see if she's actually right. So I'm going to multiply my first terms, and I get 30. My outer terms gives me a negative 20i. My inner terms give me a positive 18i. And my last terms give me a negative 12i squared, which I have to remember I squared is the same as negative 1, so it gives me a negative 12 times a negative 1, which is positive 12. All right, so now I can combine like terms, and I find that my two real values are 30 and 12, which gives me 42, and my complex values are negative 20 plus 18, which is a negative 2i. So in this instance, it would appear that Princess Polly is wrong, and that we have 42 minus 2i as our actual value. Okay, question 2. Oh boy. Princess Polly showed that 9 plus 2i times the quantity 3 minus 5i is equal, and then actually this is really weird here. This is 9 plus 2i times the quantity of 3 minus 5i minus 9 plus I times the quantity 3 plus 5i. Okay, so this is all one expression. It's these two terms multiplied together, and then subtracting these two terms multiplied together. Those are equal to 15 plus 9i. Okay, so let's just kind of follow her procedure here. Step 1, this is given, so we're doing a proof. It's given. Step 2, what she's doing is she's factoring out that 3 plus 5i. So let's go ahead and do that to make sure that her statement is correct. So when I factor out that 3 minus 5i, okay, if I factor it out of here, I get 9 plus 2i, okay? And then if I factor it out of here, I get 9 plus I, but I have to subtract that whole thing. So minus the quantity of 9 plus I. Okay, so I have to be pretty careful here because this negative is going to have to be distributed to both of these. So this becomes 9 plus 2i minus 9 minus I. Okay, and she has minus 9 plus I. So I can tell you right now that while factoring out 3 minus 5i is a correct step, and the correct reason, her statement, what she did wrong right here, is going to make everything else incorrect. So we can scroll down and say she made her error in statement 2. Okay. Question 3. Princess Polly states that the product of 7/4 x plus 9/4 I and 7/4 x minus 9/4 I is 49x squared plus 81 over 16. Okay, normally, so this is a difference of squares, right? And we've seen these before in Algebra 1. And difference in squares, if I have ax plus b times ax minus b, the difference of squares means that I will have a squared minus b squared, or ax squared minus b squared. But we are dealing with I values, and so I squared is negative 1. So that's going to change things around just a little bit, okay? So let's work through this. I've got 7/4 x plus 9/4 I times 7/4 x minus 9/4 I, okay? So let's just go ahead and we are going to go ahead and use that same ax plus b times ax minus b to get that ax squared minus b squared, but let's see where that takes us. So I know that my outer and inner terms are going to cancel out, and that's still going to happen here. So all I'm going to have as my first and last terms, I'm going to have 49x squared over 16. Okay, and then I'm going to have that minus my b squared value, which is going to be 81I squared over 16. But here's what we know. I squared is -1. Okay, so now I've got 49x squared over 16, and I'm going to add 81 over 16 instead of subtract it. So that I squared threw a little bit of a wrench into it. That is what Princess Polly calculated. So in this instance, she is correct. Okay, question 4 states that Princess Polly claims that the equation 3x minus 4i times 7x minus 8 times 3x plus 4i has 3 roots, a real root and a complex root with a multiplicity of 2, and all that, of course, being set equal to 0. The way that they've got these written is a little wonky. Sorry about that. Okay, so which statement regarding her claim is true? Well, in all actuality, we can set any of these equal to 0 and solve for it. And so we have to have 3 roots. This is the fundamental theorem of algebra. So the fundamental theorem of algebra states that if p of x is a polynomial of a degree greater than 1, then it has exactly that degree or n number of roots. So in this case, if we were to multiply all 3 of these out, we would have a polynomial, we would have a cubic polynomial, or x to the 3rd power. And so we know that we're going to have 3 roots. And then in this case, we've got a I think it's called a complex conjugate theorem as well, a complex conjugate root theorem, and that states that if a plus bi is a root of a polynomial, then the conjugate a minus bi is also going to be a root. So we're not going to have the multiplicity of 2 with -4/3 I or +4/3 I. Those are going to be their own distinct roots. So we can solve each of these, setting each of these equal to 0, and end up with 3 distinct roots. So in other words, she is not correct. The equation we can see really easily here has a root of 8/7, and then it's going to have the complex roots of 4/3 I and -4/3 I. Okay. Oops, let's see. Click. There we go. All right. So question 5 wants us to work through what the correct answer for number 2 was. And they want us to do it in proof form. So statement, reason, statement, reason. So I have gone ahead and done that. And we previously decided that we were going to factor out the 3 minus 5i. So let's scroll up so we give ourselves a little room here. And let's I'm just going to say S and R, okay? And so when we did that, we ended up with 3 minus 5i multiplied by 9 plus 2i minus the quantity 9 plus I. Okay, and our reason for that was factor 3 minus 5i, okay? And then the next step is that 3 minus 5i, and I'm going to distribute that negative sign. So 9 plus 2i minus 9 minus I. And that's the distributive property. Okay. 3 minus 5 I, and I am going to rearrange then 3 minus 5i. I'm going to say that this is 9 minus 9 plus 2i minus I. This is the commutative property where you can rearrange. Okay, and 3 minus 5i. I am going to combine like terms so that I get 0 for my real terms here, and then my imaginary terms just go to I. Okay, and that is combine like terms. Okay, the next thing I want to go ahead and do is use the distributive property again and multiply I through each of these. So I get 3i minus 5i squared. So this is the distributive. Okay. And then, let's see, I'm going to go ahead and substitute I squared equals -1. So 3i minus 5 times -1 is substitute, oops, substitute I squared equals -1, okay? And then simplify. Let's go up and just do it here real quick, S and R. So if I simplify this, I get 3i plus 5. Let's simplify. And then I can rearrange it into how we're used to seeing it, 5 plus 3i, and back to the commutative property. Okay, so that is what we're looking for number 5. I wanted you to see that, but I'm going to go ahead and let you get away with just typing that you watched it all in the recording. Or you can write it out if you really want to. Okay, and last but not least, if we go to number 6, they say checking her work in number 5. I believe in this one they actually meant to check her work for number 4 with that fundamental theorem of algebra and the complex conjugate root theorem. So those are the two theorems, the fundamental theorem of algebra and the complex conjugate root theorem, that we can use to prove that she was slightly incorrect in her reasoning. And that's what you should put for number 6. Okay, so I've gone ahead and typed that out for you, what you should be looking at here, and I think I explained it earlier. So thank you again for giving me about 15 minutes of your time. I will see you back here for lesson 3. Take care.